You remember at the outset, I told you there are two ways we do this: confidence intervals and p-values. We've already talked about the confidence interval route. Now let's talk about how we're going to use p-values. What I propose to do next is walk you through basically, the logic of statistical inference, making sure you understand how this process works and how we're going to make statistical decisions. Experience suggests to me the best way to walk you through this is to walk through an example with you together. And so, ladies and gentlemen, congratulate me. I've just been given a tremendous sum of money by the Pfizer Corporation to test the brand new anti-diarrhea medication, Kaopectate 9. We're expecting great things out of Kaopectate 9. They even have a marketing campaign all ginned up under the slogan, "We stop you up so you can get going." Kind of clever, don't you think? But we don't actually get to use that slogan unless we show the medication actually works. And so, thank you. You're all volunteers for my research study. I appreciate your efforts. And by the way, you all have massive explosive diarrhea. Don't anyone leave your chair. In this, listen to the words, randomized, double-blind study, Group A over here to my right, you are getting, unbeknownst to you, the wonder drug Kaopectate 9. Group B over here on my left, you're getting, unbeknownst to you, little white sugar pill, placebo. What I'm going to do is simply follow both groups forward in time and see how long it is until we have cessation of diarrhea, as signified perhaps by 2 solid stools in a row. That's my study design. Before I can proceed and finish my research and then do the analysis, I have to do one other step. I have to define the null hypothesis. The null hypothesis seems to be confusing for many people, but it really shouldn't be. The null hypothesis is easily described. The null hypothesis is simply the opposite of what you're looking for. In short, if in this study I want to show the drug works, then the null hypothesis is the opposite. The drug doesn't work. That's it. The null hypothesis is a statement that any differences between the two groups are due to random factors, due to chance. In this case, not due to the drug. That is, if I find differences, it's not because the drug worked. What is the null hypothesis? Again, simply the opposite of what you're looking for. In this study, the drug doesn't work. Now, let's be clear why we do this odd thing. I don't get to demonstrate the drug works, because as Aristotle showed us several millennia ago, under logic, you can't prove something. All you can do is disprove something. I therefore can't show the drug works. All I can do is disprove the proposition the drug doesn't work. That's what I'm doing with my statistics. I don't get to show the drug works. I try to disprove the drug doesn't work. Disprove the drug doesn't work. Does that sound like a double negative to anybody? Sure. Well, double negatives are terrible English, but they're great statistics. This is how the system works. We don't demonstrate the drug works. We disprove the drug doesn't work. Now, when we're talking about null hypotheses, you may see some vocabulary referring to one-tailed versus two-tailed null hypotheses. I'm going to take a brief moment and tell you what these are, but frankly, I don't really want you to worry about these. These are not a core issue for your Step 2 CK exam, but just for your general information, let me tell you what we're talking about here. A one-tailed null hypothesis is one where there's only one way to disprove it. A two-tailed null hypothesis is one where there's two separate ways to disprove it. Consider the following proposition. Men and women are the same height. Well, let's see. If men are taller, that's wrong. If women are taller, that's wrong. So that's two ways I could prove the proposition wrong. Therefore, the proposition men and women are the same height is a two-tailed null hypothesis. Holding that in mind, compare it to the following. Men are not taller than women. Well, if men are taller than women, then the proposition's wrong. What if women are taller than men? Then that doesn't disprove the proposition. There's therefore only one way to disprove the proposition, if men are in fact taller. Therefore, that is a one-tailed null hypothesis. One-tailed versus two-tailed is simply how many ways can you disprove it. If you could talk about something being either greater than or less than, then that's two-tailed. If you could talk about something being only greater than, or alternatively only less than, that's one-tailed. Now you know, but again, I don't believe that's a core issue for you on your exam. All we need to have in mind is the null hypothesis is the opposite of what you're looking for. Now what? Well, with the null hypothesis defined, we conduct our research. I hand out the medication to both groups, the treatment and placebo group, and when both groups have abatement of their diarrhea, we're now done with the data collection phase. I excuse my subjects, I can send them about their lives, and now I sit down and I organize my data in the appropriate format and form. When it's organized sufficiently, I can then enter the data into a computer where I will do analysis. What happens in the computer? Why do you care? It's not on your test. All you need to worry about is not what happens in the computer, but what comes out of the computer. What comes out of the computer are a bunch of letters. T as in t-test, F as in f-test, R as in a correlation coefficient, or even Greek letters as in chi-squared. When you see any or all of these letters on an exam question, here's what I want you to do. I want you to stop, take a deep breath, focus, and then ignore them completely, because there's nothing there that will help you at all. There's one and only one letter you need to focus on, and you know what that letter is. It's, of course, the p-value. The p-value in this context has nothing whatsoever to do with urology, but everything to do with how we make statistical decisions. Because let there be no doubt in your mind, that's what this process is about, making decisions. We don't do statistics just because we like it. We don't do statistics because it's fun. We do statistics to help ourselves make good, clear decisions. Now, have you ever actually sat down and thought about how it is we make decisions? Have you ever actually sat down and worked through that process? Well, if you actually step aside from thinking about statistics and just think about basic decision making, it occurs by a simple three-step process. First, you define a proposition. Secondly, you get empirical data. Third, you compare the empirical data to the pre-existing proposition, and by that comparison, the decision is simply made. You have a standard, you have data, you compare, and you get a decision rendered. It's as simple as, hey, let's go on a picnic. Wouldn't that be fun? A picnic. Wouldn't that be fun? But let's agree, here comes the standard, if it's raining, we won't go. Everybody got that? If it's raining, no go. Now notice this proposition is put in place today before we ever know what the weather's going to be tomorrow. And then fast forward, tomorrow comes. I look outside and it's raining cats and dogs, and so we don't go. I take the empirical data, the rain, I compare it to the pre-existing standard, and by that comparison, bang, a decision is simply rendered. Or I look outside and it's a bright sunny day, and so now we do go. Once again, empirical data, the sun, compared to the standard, and by that a decision is rendered. Notice how this process works. At the point of the actual decision, there's no real thought involved. The decision is in some real sense pre-wired based on the standard we put in place and the evidence we decide to accept. If you're confused about what the p-value is, this is why. The p-value is both of my hands. The p-value is first a standard we put in place. We call this a p-value criterion or an alpha criterion. We set this alpha criterion before the research is ever conducted. And then at the end of the research, out of the computer comes a computed p-value, also called a computed alpha. The way the process works is we simply compare the computed p-value to the p-value criterion, and by that comparison, the decision is simply rendered. With that overarching template, let's take a look at something specific. I'm going to draw your attention to the figure which you see on the screen before you. This figure is a way to get you to visualize, conceptualize what's happening as we're making our statistical decisions. First, we have to lay out what our p-value or alpha criterion is. Now, we could set this alpha criterion as high or as low as we wish, but most usually we set it at p less than or equal to 0.05. Why p less than or equal to 0.05? Well, first, it's tradition. It's what everybody else does. And when you don't know what to do in life, here's a good rule: do what everyone else around you is doing. But secondly, there's an enforcement mechanism. Would you like to get your article published? Well, this is pretty much what the editor will hold you to. If you really want to get it published, you better match the criterion of p less than or equal to 0.05. But none of that's really the reason why we end up using p less than or equal to 0.05. You want to know really why we use p less than or equal to 0.05? Let me try to explain this to you. Let's go back and think for a moment about, well, confidence intervals. If I have a 95% confidence interval, what's my chance of being right? Well, come on, that's obvious. 95% chance of being right, yes? Okay, what's my chance of being wrong then? If I have a 95% chance of being right, what's my chance of being wrong? 5%? Right. P less than or equal to 0.05. But which I want you to understand that a 95% confidence interval is basically a direct correspondent to P less than or equal to 0.05. What's the difference between confidence intervals and p-values? Simple. In confidence intervals, we're having the conversation about your chance of being right. With p-values, we're having the conversation about your chance of being wrong. But in all honesty, it's the same conversation, isn't it? Confidence intervals and p-values are merely heads and tails of the exact same coin. We're going to reach the same conclusion, make the same decision. It's simply a choice of how we want to have the conversation, confidence intervals or p-values. Why do we use p less than or equal to 0.05 for our alpha criterion most usually? Because it's the direct correspondent to a 95% confidence interval. So, if on the exam they do not specify what you should use as your alpha criterion, assume the standard p less than or equal to 0.05. If they do specify what you should use for your alpha criterion, then use what they specify, ignore the standard criterion, and go with the special criterion that is embedded for you in the question. We're going to use the standard criterion here in our example. We're going to use the alpha criterion of p less than or equal to 0.05. Okay, with that in place, now out of the computer comes my computed p-value. Let's say I get a computed p-value of p equals 0.02. I am, in the figure, and also conceptually, below the bar. P less than or equal to 0.05 is the bar. I'm now below the bar at p equals 0.02. P equals 0.02. I'm below the bar. Is that good or bad? Well, that's good. That's good because I'm below the bar. This is not a hurdle I'm trying to jump over. This is the limbo bar I'm trying to get underneath. How low can you go? All right, you want to get underneath this bar. I'm underneath the bar, and so what action do I take? Easy. I reject the null hypothesis. I reject the null hypothesis. Is that good or bad? Well, that's good. Because remember, the null hypothesis is the opposite of what I want to find. The null hypothesis in this case is the drug doesn't work. When I reject the null hypothesis, I reject the proposition the drug doesn't work, which of course leads me back where I want to be, namely, the drug works. And if all that double negative confuse you, let's go back to the basic issue. Reject null hypothesis equals the drug works. Write that down. Reject null hypothesis equals the drug works. The drug works. Eureka! I'm happy, the drug company's happy, and there's a big celebration. Everybody's happy because we're going to make a lot of money from this drug. But in the middle of this celebration, I just had one nagging thought that's causing me some concern. Here's the thought. Is it possible in my study the drug works, but out in the real world it doesn't? It's possible that in my research data this is a good drug, but out in the real world this really doesn't have benefit? Well, it's not likely, but it is possible. And if that turns out that it was true, that the drug doesn't work in the real world, well, then the decision I just made, rejecting the hypothesis, was wrong, was a mistake, was a type 1 or alpha error. Type 1 or alpha error is simply I rejected the null hypothesis, but I should not have. Now, many people seem confused as we start to talk about errors in our statistical decision making, type 1 error and type 2 error. Really, there should be no confusion here because if I'm making decisions, there's only two ways I can be wrong. I can say yes when the reality is no, type 1 error, or can I say no when the reality is yes, that's a type 2 error. I want to make sure you understand what we talk about by type 1 and type 2 errors, so let's take you out of the context of medical research. Let's put you in a different context. You're out watching a basketball game. And there you are at the basketball game cheering for your favorite team. And suddenly, tweet, the referee blows a whistle and points at your favorite player, calling a foul. Play resets based on what the referee's called. And then the game goes forward. But then, a little bit later, you watch an instant replay and you realize there was no foul. The call the referee made was clearly wrong. There was no foul. The referee made a type 1 error. The referee blew the whistle, called a foul, and there was no foul. The referee did something when you shouldn't have done something. That's a type 1 error. A little bit later, you're watching the game, and to your horror, your favorite player takes an elbow into the side of his head and goes flying in the bleachers, knocking out several fans. The referee, watching something else going on in the court, doesn't see this horrible foul. No whistle is blown, no call is made, and play proceeds as if this terrible foul never occurred. Now, clearly, the referee's made a mistake again, but a different kind of mistake. In this case, the referee's made a type 2, what we also call a beta error. In short, the referee did not blow the whistle when he should have. What's a type 1 error? When you tweet, blow the whistle, and call significant, and that turns out to be wrong. What's a type 2 error? When you didn't blow the whistle, but you should have. In this context, we've rejected the null hypothesis, we've blown the whistle, and we've declared statistical significance. Now, we know that we've done the right thing by our data, but we also realize it's possible the data don't match reality. It's possible that because we rejected the null hypothesis, we made a type 1 error. Looking at what's presented here on the slide, the box below the bar, what's the chance that we made a type 1 error? Well, that's easy. Read the p-value. 2% chance. P equals 0.02. There's therefore a 2% chance that we made a type 1 error. Wait a minute. How can we simply read the p-value and get type 1 error? Oh, that's easy, because p-value is type 1 error. I'd write that one down too. P-value equals type 1 error. Understand how this process works. First, we ask you to set a criterion as to how much type 1 error you're willing to accept. 5%? Okay. And now out of the computer comes an estimate of 2% type 1 error. You're willing to accept 5. The computer tells you have 2%. Do you take the chance? Of course you do. You've matched the criterion. You've overmatched the criterion. You're willing to put up with 5% chance of error. You have 2% chance of error. You take the chance. That's how the system works. Simple, pure decision making. Criterion, data, you simply make the comparison and make the decision. But that's only one possible outcome from my research. Here's the second. This time, a different outcome. P equals 0.13. P equals 0.13. I'm now above, not below the bar. I'm above, not below. I haven't matched my criterion. What action do I take? I do not reject the null hypothesis. Please note, I do not accept the null hypothesis. I merely fail to reject it. The decision here is the same decision that a jury is asked to reach in a court of law. No jury will ever find you innocent. They don't have that option. The only option they have is guilty versus not guilty. In this case, our decisions are to reject or to fail to reject. There's a big difference between you didn't do the crime and we don't have enough evidence to prove it. When we're not rejecting, we're saying we don't have enough evidence to prove it here. So, we are not rejecting the null hypothesis. What's the chance that we made a type 1 error? Oh, that's obvious. 0. Because you can only make a type 1 error if you do reject the null hypothesis. Having failed to reject the null hypothesis, there's a 0 chance of a type 1 error. That doesn't mean, however, we're error-free, because we could have made a type 2 or beta error. Remembering that type 2 or beta error is when you fail to reject, but in fact you should have. And once again, the whole point about type 2 error, as for type 1, is it's the data don't match reality. In the study, it doesn't look like the drug works, but in the real world, the drug actually does work. It's a good drug. So failing to reject the null hypothesis in the study constitutes a type 2, that is a beta error. All right, now using the information in the box above the bar here, what's the chance that I made a type 2 or a beta error? Well, the best answer to that question, what's the chance I made a type 2 error, is, gee, I don't know. Because there's no information here at all to tell you the chance of making a type 2 error. Those of you looking at the p-value and thinking 13% chance of a type 1 error, absolutely not. Those of you thinking 1 minus the p-value, 87% chance of a type 2 error, absolutely not as well. Stop looking at the p-value. Why? Because I asked you about type 2 error, and p-value, you remember, is purely about type 1 error. P-value gives you no information whatsoever about type 1 error. And so, that was a quick run through the logic of statistics. Let's do a quick review. You first set your alpha criterion, usually p less than or equal to 0.05. If I'm below the bar, I reject the null hypothesis, knowing I might have made a type 1 error. What's the chance I might have made a type 1 error? That's easy. Read the p-value. If I'm above the bar, I do not reject the null hypothesis, knowing I might have made a type 2 error. What's the chance of a type 2 error? I don't know. I just know I might have made one. That's it. Basic logic of statistics. And please note, folks, this is not about math. This is about logic. If you think about statistics as mathematics, you're missing actually the key point here. It's about logic, it's about decision making, not really about mathematical calculation. That's simply the technical mechanics by which the logic occurs. Now, a couple closeout questions. Type 1 versus type 2 error. Type 1 versus type 2 error. Which is worse, type 1 or type 2 error? Well, we usually think that type 1 error is first. Think about it this way. If you're Catholic, or even if you're not, Catholics talk about two kinds of sins. Sins of commission, when you've done something you shouldn't have done, and sins of omission, when you haven't done something you should have done. A sin of commission, I look you in the eye and I lie. A sin of omission, I just forget to tell you something that I should have told you. Which feels worse? Well, for most people, the lie is worse. That's a type 1 error. Type 1 error is usually considered the worst sin. Okay, second issue. Suppose you get the results below the bar here. P equals 0.02. You decide that kaopectate 9 is a great drug, and after approval by Food and Drug Administration, you proceed to prescribe this to all your patients with severe persistent diarrhea. Patient comes in with severe diarrhea, you give them a prescription for and a sample of kaopectate 9. The patient looks at what you've given them and says, "Doc, I know this drug worked in the research, but boy, what's the chance this drug is going to work for me? What's the chance the drug is going to help me personally get better?" Based on the information presented below the bar here, your best reply to the patient would be, listen, gee, I have no idea. Because those of you looking at the p-value, stop it again. The p-value does not answer your patient's question. So let's think more about what this p-value gives us. The p-value is basically the referee in this game of science that we're playing. The p-value is the whistle that blows and declares significant or non-significant. It's how we're going to make our statistical decisions. The p-value in this context gives us the chance that we made a type 1 error, because remember, that's a decision criterion. When we're below the type 1 error we're willing to accept, we're willing to take the chance. What the p-value does not give us is what your patient asks you for, namely clinical significance. Now let's try to draw this distinction, which I mentioned before, but now I want to present more formally. There's two decisions that have to be made here. First, statistical significance, namely, is there a difference? As I'm looking at the cessation of diarrhea in group 1 versus group 2, is there a difference? And the p-value will answer that question for me. But once I have that question answered, there's a different question, namely, does the difference I observe matter? Does the difference that I see actually matter in a practical, clinical, dare I say, day-to-day basis? In general, statisticians won't talk with you about clinical significance because it's not their purview. Statisticians are good about helping you understand statistical significance, whether or not there's a difference. You are frankly in charge of deciding clinical significance. Does the difference matter? Let me try to walk this through with you with two examples, try to illustrate the point. Suppose you're reading a research article comparing two different antihypertensive agents, drug A and drug B. And you see in reading the research article that drug A works better than drug B, and that's significant at the standard 0.05 level. Drug A works better. What we have now is statistical significance. Good. But now we have to answer the clinical significance question, namely, is this a difference that matters? Well, as you look more detail at the data, you notice that drug A does lower blood pressure more than drug B, but it only lowers it 0.5% more than drug B. That's a difference that is statistically significant, but now, is that really clinically significant? Well, most people decide, no, it's not. There's an illustration of statistical significance, yes, but clinical significance, no. Once again, statistical significance says, is there a difference? Clinical significance says, does this difference matter? Let me try one other illustration. I'm completing, as a part of my own research, analysis of data collected from first and second year residents in training in the United States. We sent out a survey all to residents, a nice sample all across the United States, and got a pretty good response rate from 3,500 residents. They completed a very extensive questionnaire telling us about what their life was like during these first 2 years of residency training. In the course of analyzing that data, we found out some things that really people didn't know before, including one I want to share with you now. As we analyzed the data, we discovered that in just about every medical specialty, on average, men work longer hours every week than women. Week in and week out, men work longer than women. And that finding is significant at the p less than or equal to 0.0001 level. It is highly statistically significant. Men work longer than women. And so now you know, men, I'm sorry, but when you show up for residency training, week in and week out, on average, you're going to be putting in more time than the women. Every week, about 13 additional minutes more than the women do. Oh, let's talk about the clinical significance question, shall we? That difference is highly statistically significant, but 13 additional minutes. Does that really matter on a practical basis? Is that enough of a difference that you really care about? Well, I know occasionally somebody does, but usually most people say no. There's an illustration again of, yes, statistical significance, there is a difference, but no clinical significance. The difference doesn't matter. When your patient says, Doc, what's the chance I particularly am going to benefit? They're not asking the statistical significance question, they're asking the clinical significance question. Those of you that were thinking about the p-value, p equals 0.02, and we're thinking about telling the patient there's a 98% chance you'll benefit, that's absolutely wrong. You can't get that from the p-value. The p-value tells us statistical significance only. It does not tell us the chance an individual patient will benefit. It does not tell us the percentage of patients who will benefit. It does not tell us the degree of benefit expected for a given patient. All the p-value tells us is the chance that we're wrong if we reject the null hypothesis. Now, if you want to answer your patient's question, what's the chance that I personally am going to benefit? Yes, you can do that. You look beyond the p-value, you read the actual research article, and in there you might find a table of data. On that table of data, you might see something that says, out of the 100 people that we gave kaopectate 9 to, 95% had relief of symptoms. Now, can you answer that patient's question? Yes. Based on that data, not the p-value, you have a 95% chance of getting better. P-value answers the first question, statistical significance. You have to look at the actual data to answer the second question, clinical significance. I next want to turn our attention to a fairly arcane but still important concept in statistics, statistical power. There's a lot that can be said about statistical power, but fortunately, most of it doesn't show up in your Step 2 CK exam. So I just want to talk through the basics so you understand how to answer these issues when they do appear. First, I need you to understand what we mean by the concept of statistical power. Well, this is fairly easily defined. Power is simply the capacity to tell a difference. Power is your ability to see what's going on, in short. Power in this context means exactly what power meant when you're back in histology lab. You're looking through the microscope at a slide. I say to you, is that one cell or two cells? You say, gee, I can't tell. So you increase the power. Your ability to focus and see the detail of what's going on is what power is all about. You should know that, too, power is directly related to type 2 error by the simple formula. 1 minus power gives you beta, or 1 minus beta gives you power, or power plus beta equals 1. I don't care how you remember it, just remember that power and beta are directly related. The only way on your Step 2 CK exam they could ever ask you to come up with a number for beta is if they give you power. If they tell you, for example, the power is 80%, and we didn't reject the null hypothesis, you know clearly that the chance of type 2 error is 20%. 1 minus 80% gives you 20%. You should also know that there are three things that increase power, three things that give us more power. The first is fairly obvious: larger sample size. The larger the sample size, the better chance we have of seeing what's going on. The more information we have, the easier it is to see what's happening around us. I always think about the sample size in this case as almost illumination. It gives us enough light to see what's happening. The second thing that increases power is called effect size. And that's a technical term that seems obscure at first, but this is really all it means. Effect size is how large is the thing you're looking for. If the thing you're looking for is big, you're more likely to find it, hence more power. If the thing you're looking for is small, you're less likely to find it, hence less power. Concretely, two animals have escaped from the local zoo, an elephant and a mouse. Which one do you think we're more likely to find? Right, the elephant. Why? Larger effect size. If you're looking for something big, you're simply more likely to find it. Third, if your alpha criterion is easier, weaker, if it is, in short, easier to reject the null hypothesis, you have more power. Now stop for a moment. I'm talking about the alpha criterion, the bar. I'm not talking about the computed alpha, what comes out of the computer. I'm talking about the standard you adopt at the outset. Remembering the standard is usually p less than or equal to 0.05, but I remind you we could set the standard high or low however we wish. If it's easier to reject the null hypothesis, we have more power. So to make sure you're with me, let's do a simple question. Which of the following alpha criterion has more power? 0.2, 0.1, 0.05, 0.01, or 0.001. Again, we're not talking about what comes out of the computer. We're talking about the predetermined standard. Well, the answer here, of course, is A. A has the greatest power because that's the bar that's easiest to get under. It's easier to reject the null hypothesis. But wait a minute. Doesn't that give me more chance of a type 1 error? Yes. And once again, you have a trade-off here. If you want to seriously avoid type 1 error, you're going to, as you make your criterion more stringent, reduce the power that you have. Let me frame it for you this way. If avoiding type 1 error is so important, and it is, why do we use such a measly criterion, a p less than or equal to 0.05? Why don't we use, as you see on your slide, the criterion of p less than or equal to 0.000000000000001? Why don't we use that strong criterion? Well, the answer is clear. We don't have that kind of power. That criterion would cause us to miss things that really matter. That criterion would cause us to say there is no difference for things that frankly have major and important difference in the real world. So understand p less than or equal to 0.05 is basically a compromise number. It's a number we pick to, one, avoid type 1 error, but at the same time have enough power to see what's going on. If all that confuses you, fall back on the familiar key things I want you to remember here, namely, what is power? Easy. Ability, capacity, that is, to tell a difference. Power is directly related to which kind of error? To type 2 error. 1 minus power gives you beta. And what are the three things that increase power? If you have a larger sample size, if you have an increased effect size, looking for something larger, and if your alpha criterion is weaker, it's easy to reject the null hypothesis, then you have more power.